Hi everyone, today we are going to talk about support vector machines. This is another technique for classification purposes, and as we will see later today, it gives us a lot of flexibility for situations where we have classes with overlaps and not necessarily linear boundaries between them. Before we get into this discussion, let's have an overview of what we have talked about so far. So we started our conversation on classification techniques by discussing logistic regression, which is more like a linear technique. We extended that to linear discriminant analysis, LDA, and we saw that it allows us to classify observations into classes where there are linear boundaries between different classes so that you can separate them with hyperplanes. We extended that to nonlinear cases by discussing QDA, and we saw that at the expense of having more parameters to choose, you're going to be able to get a higher level of flexibility. Lastly, we talk about KNN, and we discussed the shortcomings of LDA and QDA in a sense that there are some assumptions that we have to make, and if those assumptions are not valid, then the technique is not going to lead to desirable outcomes. In situations where we cannot have any sort of underlying assumptions about our classes, KNN would be a good technique. It's a very simple technique. It just requires one parameter, that K, the number of neighbors, to be determined by you as a data scientist. And beyond that, you can basically apply to any linear or nonlinear class boundaries. Today, we're going to talk about support vector machines, which is another very powerful technique for classification purposes. Okay, so let's have a little bit of history first. SVMs, support vector machines, were introduced in the 90s for classification purposes. They were essentially a generalization of a classifier which had a much simpler structure known as maximal margin classifier. This classifier assumes that the classes are linearly separable and there are no overlaps between the observations. This obviously is a very strong assumption. A different classifier known as support vector classifier extended that concept of maximal margin classifier by allowing some overlap between different classes. In other words, some misclassification by this classifier technique. Support vector machines extend that even further by allowing classes to have nonlinear boundaries. So you can now have classes that have overlaps with one another, leading you to have misclassification errors. And at the same time, the boundaries do not need to be linear anymore. So this would be a very powerful technique and very, very generalizable to a lot of different scenarios. One point of caution in the literature, by mistake, both support vector classifiers and support vector machines are referred to as SVM. It's important that you understand the difference between the two. Support vector classifiers and support vector machines both allow for misclassification errors, so a little bit of overlap between different classes, but support vector classifiers assume that the boundaries are linear. Support vector machines, SVMs, allow boundaries to be nonlinear. So this is the main difference between the two. All right, let's start with the basics. You have a series of data observations that belong to either of two classes, class blue or class red. Your objective is to find a linear line or a hyperplane in a higher dimensional space to separate these observations. Now, in the next few slides, for demonstration purposes, I am assuming that my data instances are two-dimensional. This doesn't have to be the case, though. In general, you can have a higher dimensional data set. It's just difficult to illustrate it that way. So imagine this is the case that I have. I have class blue and I have class red. And my objective is to find this particular line. W1x1 plus W2x2 equals B. This line is a line that classifies these observations to either class blue or class red perfectly, meaning that for every observation belonging to class blue, the observation lies above that line, and all the observations that belong to class red, they lie below that particular line. Mathematically, we can say for all blue data instances, W1x1 plus W2x2 would be greater than or equal to b, whereas for every data instance that belongs to class red, this relationship would be less than or equal to b. Now we can state the previous equation in a different way. I can define a function f of x, which is going to be w1x1 plus w2x2 minus b. Then for every blue data instance, I would like the value of f at that particular data instance to be positive. And for every red data instance, I want that value to be negative. Naturally, if that value is close to zero, either positive or negative, that means that particular data instance is very close to the boundary. Whereas if that value is much larger positive value or a much larger negative value, that means that the data instance is far away from the boundary, which is another indication that we are confident in our classification. If you find a data observation and its f value becomes like 0.001, yes, based on this function, it does belong to class blue, but the question is how confident are you in your classification? Whereas if that f value turns out to be 10,000, obviously you are a lot more confident. One of the challenges that we have is in situations where the classes are very well separable, like the example I showed you on the previous slide, there can be an infinite number of lines or hyperplanes in a more general case that would achieve that particular objective, meaning that all blue data instances would be on one side and all red data instances would be on the other side. So the question is, how can we find the best hyperplane and what would be the definition of that best hyperplane? In order to mathematically model this problem, we can actually formulate it in the form of an optimization problem. Consider what we're trying to achieve with our classifier. If my discriminating function is f of x, I would like the value of f of x to be positive for all blue data instances and negative for all red data instances. In order to formulate this as an optimization problem, what I can do is this. I can say for every blue data instance, I would like f of x to be positive. However, I will allow certain level of error. So f of x maybe by itself is not positive, but if I add a positive value to it, such as e of I, which is the error for that particular observation, that becomes positive. I will do the same thing for red data instances. So I would like f of x to be negative, but if it's not negative on its own, I would say I would like f of x minus some positive value to be negative. Now my objective is to minimize these error values and set them close to zero as much as possible. So essentially I would say I would like to minimize this summation of all the errors, which is my objective function, subject to this constraint and this constraint, which basically indicates the difference of that f of x from 0, and a non-negativity constraint saying that all EIs have to be positive. Obviously, under ideal situations, all EIs would be 0, meaning that all my f of x's for blue data instances would be positive. All f of x's for red data instances would be negative, which is the ideal situation. Now, you might think to yourself, great, I'm going to solve that optimization problem. It's a linear problem, so it's easy to solve, and I will find the best boundary between the two classes. Unfortunately, that's not always the case. In situations where the classes are very well separable, you may end up finding an infinite number of boundaries. Let me show you through an example. Imagine you have two classes. One would be class red, just like I showed you on the previous slide. The other one would be class blue. Now let's think about that optimization problem. What is it trying to solve? It's trying to solve for a boundary for which all the EI's individual errors would be 0. This would be that line, because for every blue data instance, all the f of x's would be positive, so EI's are 0. And for the red data instances, all the f of x's would be negative. Again, EI's would be 0. So that satisfies the optimum value of that objective function. However, the same thing can be said about this line, and the same thing can be said about this line and this line. So which one is the best boundary? Maximum margin classifier actually tries to answer that, tries to find the best boundary for us. And in order to do that, it looks into the notion of margin. So ideally, we would like this optimal boundary to be as far from the data points as possible, because if it's close to data points, that means that we have less confidence in our classification. So what we do is for every particular line in a two-dimensional space or hyperplane in a higher dimensional space, we compute the distances from all individual data instances to that particular plane or line. The smallest distance that we have to that line, to that boundary, we call it the margin. And then maximum margin classifier will try to find a boundary line or hyperplane for which the margin is the largest. This will give us the highest confidence in our classification purposes. Let's look at it graphically. Consider this example. I have, again, as before, a class blue and a class red. And I have this margin from here to here between the two classes. So theoretically, any line that lies within that margin would be a classifier for me. But since I'm looking for the classifier that has the largest margin, in other words, the largest distance between all the observations in the two classes, graphically you can see that this green line that I'm showing here, this guy here, this would be the best solution because it is as far away from both classes as possible. So imagine this decision boundary is W1 x1 plus W2 x2 equals B, and I'm assuming that the smallest distance of class blue to this particular boundary is M, and the smallest distance of class red to that particular boundary again would be M. So this means that the line that I have at the edge of class blue can be expressed as W1 x1 plus W2 x2 equals B plus M. B would be the parameter associated with the decision boundary, and M would be that smallest margin between the class and that decision boundary. Likewise, the line at the edge of class red would be the same equation, except that here I would have B minus M. Now, you notice that we have some observations that have the exact same distance from that maximal margin hyperplane. In SVM terminology, we refer to these as the support vectors. Support vectors are very critical because if you change the position of one of the support vectors, the entire boundary, the entire decision hyperplane will change, despite the fact that others don't have that same effect. Consider this example. If I change the location of this particular observation and move it, for example, somewhere here, you can imagine that this green line, which is my decision boundary, would have to change. However, if I take this particular observation and move it anywhere I want, nothing is going to happen to my decision boundary. Still, my maximal decision boundary is going to be the green line, and everything is going to be the same as before. So support vectors are the critical observations that will determine where the boundary is going to lie and how it's going to look like. Now let's remember from linear algebra. This line, which is a decision boundary, as I showed you on the previous slide, is W1 x1 plus W2 x2 equals B. And this line is the same equation except that W1 x1 plus W2 x2 equals B plus M, and this one is B minus M. If I create this vector W, which consists of coefficients W1 and W2, from linear algebra, you remember that this vector of W is perpendicular to this particular line, as I am showing here. And then the distance of this line, the green line that is, the decision boundary, to the origin along the lines of W would be B divided by norm of W, the 2 norm in this case. Following the same logic, the distance of this edge line for class blue to the origin along the lines of W would be b plus m divided by 2 norm of w, and for this one is going to be b minus m divided by 2 norm of w. 2 norm is going to be square root of w1 squared plus w2 squared plus w3 squared, so on. In this particular two-dimensional case, it's just going to be the square root of w1 squared plus w2 squared. So the margin between the two boundary edges would be this distance, which is b plus m divided by norm of w, minus this distance, which is b minus m divided by norm of w. If you simplify this, it will be 2m divided by norm of w. Because we can always normalize and rescale our observations, let's assume for simplicity we can do that so that m becomes 1. So the distance between the two edge margins, the edge lines, would be 2 divided by norm of w. So our objective here is to find those wi coefficients, because my decision function in this case would be my f of x, which is summation of all the wi's times xi's minus that constant b. It can be shown that these wi's are related to the training data set. So essentially you can say all the wi's are going to be a function of your training data, and this way you can develop multiple linear equations in order to solve those coefficients. However, we have a better way to solve this, which is through mathematical optimization. So what we do is this: we formulate it in the form of a minimization problem, which is minimizing the 2 norm of that vector w. Remember, my objective in maximum margin classifier is I would like to maximize the margin, which was 2 divided by norm of w. When I'm using 2 norm, this is going to be square root of summation of all the wi's. So in order to mathematically formulate this, I would say to maximize margin, which is this term, I would like to minimize the summation of wi squared. Subject to what constraints? I want to make sure that for every class, either blue or red, I make the right decisions. Meaning that w transpose xi minus b is greater than 1 for class blue, and w transpose xi minus b is greater than minus 1 for class red. Notice that here, unlike what I showed you on the previous slides, instead of saying positive and negative, I'm saying greater than plus 1, less than minus 1. Why is it? Because it doesn't suffice for me to be positive and negative anymore. Not only I want all the blue observations to be on one side of that boundary, I also want them to be away from the boundary. So before, let me use a different color, before it would be okay for me for blue observations to be here. As long as they were above that boundary, I would be okay. So in that case, I would say for all observations belonging to class blue, let's say this is class blue and this is class red, this left-hand side should be positive. Right now, however, I'm requiring a different thing. I'm saying not only I want to be on the other side of the line, I actually want to have a certain distance, a certain margin. So I want a line for which the blue observations are here, which means this value is going to be greater than 1 now instead of greater than 0. And for red, it would be less than or equal to minus 1, unlike the previous cases that I showed you, which was less than or equal to 0. Now, I have kind of two constraints, because one of them is for class blue, one of them is for class red. And if I assume that class blue is 1, class red is minus 1, and again, notice that this doesn't matter. You can assign any number you want to. But based on the numbers that I have assigned, I can actually combine these together and basically rewrite these two constraints in this form. For every observation, I want yi, the outcome of that observation, the class to which that observation belongs, times this term to be greater than 1. Does that exactly give me these two constraints? Absolutely. Take a look at observations belonging to class blue. For them, yi is going to be +1. So that means this term has to be greater than 1, which is exactly what I have here. How about class red? This is going to be -1. So -1 times this term is going to be greater than 1, meaning that this term is going to be less than -1, which is exactly the equation that I have here. Here I have two variables. One of them is xi, which are the independent variables of the observation. The other one is yi, which is the class to which that observation belongs. And you notice that I'm multiplying them by one another in this constraint. This makes this optimization problem a quadratic problem. So it's not as linear, it's not a linear problem like before. However, this is still okay because quadratic optimization problems are still tractable and we can actually achieve global optimum. So that doesn't pose any problems for us. Now you might be quite happy with the maximum margin classifier. It gives us a linear decision boundary and it finds it in such a way that it has the maximum margin between the two classes. That is perfect. So you might be wondering, why do we need to know any additional classifiers? Well, there are two problems. One is that not all data sets are linearly separable. So this notion of having a linear decision boundary doesn't necessarily apply to every problem. Imagine you have a situation like this. This is your class blue. This is your class red. There is no linear line that can perfectly separate these two classes. Another problem is sometimes when you solve for a decision boundary using maximum margin classifier, you end up with a decision boundary whose margin to different classes is actually pretty small. Why is this a problem? Because when the margin is small, your confidence in classification would be low. Again, imagine a problem like this. Imagine you have class blue like this, and you have class red like this. Now here, the maximum margin classifier might actually recommend a line like this. Imagine this is a linear line that separates class blue from class red. This is a linear line, so that's okay. However, the margin between the two classes is actually pretty small. So for any type of observation that is in this region, I'm not too confident about my classification. I am classifying, for example, this guy as belonging to class blue, but it's pretty close to the margin, to the decision boundary, so it might as well be class red. In situations like this, what we do is we introduce a certain level of relaxation, in a sense that we say we would like to find a hyperplane that almost separates the classes. For example, in this particular case, this might be that hyperplane. Notice that in these two instances, it actually fails to classify them correctly, but that might be okay. That might be acceptable for me, that level of misclassification. Or for example, in this second case, you might be able to find a line that has a wider margin between the two classes, despite the fact that in a few instances it actually misclassifies individual observations as belonging to the wrong classes. This is the entire idea behind support vector classifier. So we typically formulate this as an optimization problem with relaxation. Just like before, just like what we had in maximum margin classifier, we are still trying to maximize the margin. In other words, minimize the 2 norm of vector W. However, instead of saying that my yi times this term has to be greater than 1, I would say it has to be greater than 1 minus some positive error value that I called ei. And then what I do is I try to minimize the sum of these errors. This is very similar to what I showed you previously. So again, here we introduce a certain level of relaxation. If all the EIs end up being 0, that means all the observations are being classified absolutely correctly. However, if some of them are misclassified as belonging to a different class, then some of the EIs are going to be non-zero. This optimization problem will try to find the best kind of trade-off between the two objectives, maximizing the margin by minimizing WIs and then minimizing the errors. You notice that here I multiply this second term, second objective function, by a coefficient c. This coefficient c is a weight parameter that tells my optimization problem how important misclassification is for me. So if I choose a very, very large number for c, my optimization problem understands that I'm zero tolerance about misclassification. I would like to make sure that all the EIs are close to zero or actually zero as much as possible. And even if that means that my WI is not minimized, meaning that my margin is not necessarily maximized, but my errors are going to be minimized. What does that mean? That means I will end up having a classifier which is classifying everything correctly, but it could have a very, very small margin between the two classes. On the other hand, if I choose a small value for C, I'm essentially indicating to my optimization problem that the margin is more important to me. The first objective function is critical. I am okay with certain instances of misclassification. If your C is large, that means you will be overfitting your data because misclassification is not tolerated. On the other hand, if C is small, that means chances of having overfitting of data is going to be lower. Now, of course, the support vector classifier can be used to give me like a hard decision on whether or not a particular data instance belongs to class blue or class red. However, I can actually convert this to indicate a probability instead of saying yes or no, a binary decision. In order to do this, I would actually define what I call a score. So the score of observation xi is going to be inner product of w times xi minus b. Naturally, if this S is positive, that means that I belong to class blue, and if it's negative, that means I belong to class red. Let's go back to linear algebra. If I have this particular observation point here, the distance of this observation point to this green line, which is my decision boundary, would be inner product of w and xi minus b divided by norm of w. So this would be my distance to the boundary. And if the distance is smaller, that means chances of me belonging to that particular class is lower. If the distance is larger, that means I'm farther away from the boundary, meaning that more likely to belong to class blue. Now, if I have enough observations for classes blue and red, I can assume that the distances of those observations to the decision boundary would be normally distributed. So the distances, the probability of the distance of that observation, provided the observation belongs to class B, to this green line, would be normally distributed with this standard deviation and this mean value. The mean value would be the mean distance of class blue from that decision boundary, and standard deviation would be the variation between the distances of individual observations. So by looking at it this way, I can basically find a probability of a particular observation belonging to class blue or class red. This, however, does not take into account uncertainties. If I want to take into account uncertainties, for example, certain misclassifications and things like that, I can use the Bayes theorem. So I can say, I can look at one particular observation, let's say some point x, and I find the distance of that point x to the green line, and it turns out to be d of x. Then I would say probability that x belongs to class blue, given that its distance from the boundary, decision boundary is d of x, would be the probability that I get that distance of d of x provided I belong to class blue times general probability that I belong to class blue divided by the same thing for class blue and for class red. You might wonder, what is the probability of class blue and what is the probability of class red? These are the prior probabilities. So you could look at your training data and say, hey, out of 1,000 observations, 600 belong to class blue and 400 to class red. So prior probability of class blue would be 0.6, and for class red would be 0.4. Now we saw that if the classes are not linearly separable, support vector classifier allows us to still find a linear boundary between them at the expense of having some misclassification, some, observations that are classified as belonging to the wrong class. This is okay in situations where the level of nonlinearity between the two classes is small. However, in some situations, that nonlinearity might be significant. So no matter how hard you try, you're not going to be able to find a linear boundary between the two classes. Look at this hypothetical situation here. I have classes blue and red here, which are completely intertwined in a nonlinear fashion. There is no linear boundary line that allows me to separate these two, even if I'm okay with having errors. So in situations like this, sometimes we are able to transform my input space to a different space in which now the transformed data instances are linearly separable. We call that the feature space. So all the x's that are my original space, I transform them using a transformation phi, a nonlinear transformation for the most part. In this new domain, which I call it the feature space, now the classes, the transformed classes, are linearly separable. So I can say I now have a line that has an equation of W1 phi of x1, which is x1 transformed, plus W2 phi of x2, which is x2 transformed, equals b. I can take everything to my feature space, do the classification, and then bring it back to the original space. This is the whole idea behind support vector machines, which is a further extension to support vector classifier. The idea here in terms of how to find that boundary is exactly like before. Again, I would like to maximize the margin by minimizing the 2 norm of my W matrix, W vector, and I would also like to minimize misclassification errors. The only difference that you probably observe here is that instead of saying yi times inner product of w and x minus b is greater than 1 minus error, I'm saying yi times the inner product of w and phi of x of I, meaning that x of I is transformed, minus b is going to be greater than 1 minus error. This is a nonlinear optimization problem, and the problem is that finding the global optimum with it is not always guaranteed. So sometimes, especially if the problem is not well behaved, you're going to have to use certain approximations and relaxation techniques in order to be able to find a solution. In general, however, finding the solution to this problem is not as difficult as it sounds. And as it turns out, you can actually look at a subset of your data instances, your training data instances, in order to find those particular W coefficients and B parameter. But this falls outside the scope of this particular lecture, so we're not going to get into the details of that. A lot of different software packages can find that boundary for you for support vector machines. Your job for the most part would be to decide what kernel you want to use. That nonlinear function, that function phi, is often referred to by the name of kernel. This kernel could be, for example, a polynomial shape, which is like, for example, this function. It could be a radial basis function, which provides a kind of a local behavior, or it could be a hyperbolic tangent problem. Typically, if you have a local behavior in classes, the second option, the radial basis function, would be the best one. Otherwise, you can do trial and error for which one of these kernels would give you the smallest test error, and then go with that. Before we finish this discussion, let's talk about support vector machines in multi-class situations. So far, we've been talking about having only 2 classes of blue and red. What if we have more? In multi-class situations, we have basically 2 approaches. One is the 1 versus 1 approach, in a sense that you for every individual test data, you look at classes to every pair of classes at a time. So consider this is my test observation, and I want to know what class this observation X belongs to. So first, I do a classification between blue and green. So I ignore red completely. This is the boundary. So C1 is the boundary between blue and green. Based on that boundary, my answer would be blue. Then I ignore class green, and I would say I want to do a classification between blue and red. I use SVM to derive this decision boundary. Based on this decision boundary, again, that observation belongs to class blue. And then lastly, I ignore class blue and I do a classification between green and red. Considering green and red, this is going to be my SVM decision boundary, and based on this decision boundary, X belongs to class red. So I have blue and red, and essentially I do a simple voting and I would say this observation belongs to class blue. If there is a tie, let's say you have 4 classes and this gives you 2 blues and 2 reds, then you would look into the distances, for example. You look into probabilities to decide which one would be the eventual class. The other approach would be one versus all. So here, instead of looking at every pair of classes at a time, I would look at one class versus everybody else. So again, the same problem as before. I will say I have this observation. First, I will say class blue versus everybody else. Imagine this is my decision boundary. Based on this decision boundary, it says it belongs to class blue and not everybody else, which includes both green and red, with a probability, hypothetically, let's say 0.95. And then you will do red versus everybody else and green versus everybody else. For each one, you will find a probability, and then you will basically go with the one that will give you the highest probability. So this brings us to the end of this lecture, this is the list of references that I used in this making this video presentation. I'm providing it here in case you're interested in knowing more. I encourage you to refer to these references.